Hello, my friends. We're going to start a great application of a few of the things we've talked about already. Certainly waves, certainly some interference and superposition stuff, and also this newer idea or topic of what we call resonance. Okay. Now, resonance, by definition, is what happens when you force a system at its natural frequency. Now, what does that mean? Well, forced really means pushed. Forced means pushed or made to oscillate. All right, now, natural frequency, by definition, is the frequency that a system would, well, settle at, I should say, oscillate at. I want to change this maybe to oscillate, if it were allowed to oscillate by itself. Every system has a natural frequency. Take, for example, a pendulum, right? We have a pendulum, looks like this. We displace it from its natural position, its equilibrium position, which is there. You know, we pull it back, we let it go. Well, this thing will oscillate at a certain frequency, which depends on its length. All right, take a wine glass. Not bad. We have this wine glass here in its equilibrium state, and we go blink, and we hit it on the side with our finger, and it goes. It has a certain frequency that it oscillates at all by itself. All right. You take a mass on a spring, let's say maybe hanging from the ceiling, like so, and we push it up a little like this, let it go, and it oscillates back and forth about its equilibrium position at a frequency that depends on a couple of things, actually. One is the mass of the object, and two is the stiffness, K, of the spring. Okay, so everything has a natural frequency. All right? Now, the deal is, in all these cases, here, here, and here, we said, what if we just, clink the wine glass with our finger? What if we just pull this thing away from its natural position, or its equilibrium position? What if we, pull this thing away from its natural position and let it go, right? We're talking about just letting things go. But here, in resonance, we're saying, what if we don't just let them go? What if we push them? What if we force them at the same frequency they'd oscillate at anyways? So we take this pendulum example, and let's imagine that it's a swing, right? Well, this thing oscillates at this frequency. Back and forth, back and forth. What if we happen to, right, push right there, and push right there, and push right there? Notice we're pushing, forcing, at the same frequency the system oscillates at anyway. Well, if that's a kid in the swing, that's how we make the kid go super high, right? We push at the same frequency the swing oscillates at anyways, or we force the system at its natural frequency. The result, right? What happens when we make a system resonate? Well, the result is always oscillations of large amplitude, right? The kid goes really high in the air. You can get some craziness like this. I'd like you to Google that, YouTube that is. The Tacoma Narrows Bridge. It'll knock your socks off. Okay? The bottom line. Now, we haven't mentioned this idea of, excuse me, standing waves yet for strings and pipes, but it's our next slide, our next 3 or 4 slides. All right, we're going to talk about creating things called standing waves, right? And standing waves happen because of these resonance conditions. We create a condition or conditions where we force a system at just the right frequency. And what we get are big amplitude oscillations. All right? We can create what are called standing waves. This is how all musical instrument stuff works. All right? And we're gonna look at a couple of cases how we use resonance not for horribly destructive things like this, but for beautiful things like music. Okay? Let's have a look at this next page. Now, standing waves. I'm going to show you an animation of a standing wave scenario. Okay? So, make sure you can still hear me. When we go to our little applet here, we're going to have a continuous wave, not just a pulse like we've seen before, but a wave that keeps oscillating, or a source that keeps oscillating. So this is us forcing the system with our oscillator here. All right, and what we get is a wave that travels down this, in this case, string. I don't know, it's a string, I guess, right? And the first thing that happens, and this is one of our, what do you call it? One of our, on this page back here, one of the phenomena that we're using, right? Well, we've gotten some reflection that happens at this end. All right? Now that we're reflecting these waves, there are waves coming this way and waves coming this way, and they do what we call interfere. All right? And now watch. I had to monkey around with this. I'm going to restart it. I had to monkey around with it a few times to get just the right frequency and just the right tension, which really talks about speed of the wave. But when we get it just right, there's our reflection, and we keep getting things that reflect, and then we get this interference, and notice a couple of things about how this wave looks. All right, one is that we get parts of the wave that seem like they never really move, right? Like this part right here. And we get these parts here that seem like these peaks and troughs always end up in the same place also. All right, that's why we call this a standing wave. I'm going to restart one more time. That's why it's called a standing wave, because it looks like it's not moving. It really is. It's really waves that are moving in both directions at the same time that keep on interfering. Is that thing going to be, yep, right at the same spot. Now notice what else happens. Because we did this just right, we're actually getting resonance. And if you notice, what happens in this resonance is that these waves, these peaks and troughs, keep getting taller and taller. Right? We keep getting more and more amplitude. Now, this isn't perfect, and eventually it's going to end up getting smaller and smaller. But if we did this just right, what we get is really almost an uncontrollable increase in the amplitude of these waves. Okay? So when we go back to here, we're mixing really three phenomena when we get these standing waves. One is reflection. Two is interference. And three is resonance. Okay? And here's what we just saw. We had two waves traveling in opposite directions. They keep interfering, sometimes constructively, then destructively, then constructively again, right? If I go back to this thing, I can probably pause it right here. Oh, look, it went all the way down to, after a while. Never mind. Yeah, I understand it takes a little while. But I'm going to try to pause at just the right time. Good, good. Good. So when we step through this, we'll see that here's a case where the two waves have interfered completely destructively. And as we step a little farther, well, here they've interfered constructively, right? Here's our incident wave. It only has that amplitude. But our interference pattern has that amplitude, which is twice that big. There's a constructive interference, right? We keep stepping forward. Hey, move it. We keep stepping forward, and we'll get back to a place where the waves interfere destructively. And then constructively again. Okay, so we get that pattern of constructive, destructive, constructive, destructive. Okay? Come back. Now, a standing wave has some characteristic parts. Two main parts we have to talk about. I pointed to one of those parts on this animation, right? That part right here, the part that play. Never seems to move, never seems to oscillate. That part we call a node. So there's a node here, it says node, and here, and here. Well, really, and here. And then this part up here, where it's always a peak, well, and I'm going to do this because I'm going to say sometimes it looks like that, right? We saw the wave sometimes look like that. We call this an antinode. And here is an antinode. And here is an antinode. And here is an antinode. Got me? Those are the two main parts. Node, antinode. That's a must in terms of vocab. Okay? Yeah, sure. Yep. Sorry. Good. Now, some systems that we can set up standing waves on. Well, like we showed in that animation, we can set them up on strings or springs. All right? And the rule is, if we're going to have a standing wave, imagine a guitar string of length L. Well, each end of a guitar string slash harp string, piano string, violin string, cello string, each end of that string is locked down, tied, physically held down. So that means they're not allowed to oscillate. There must be a node at each end of a string. Fair enough? So, if we pluck this string, the most kind of fundamental pattern we can get for a standing wave looks like this. It oscillates a ton in the middle, not at all at the end, and of course it would oscillate between the solid sort of look here and the opposite of that here, right? The string is vibrating back and forth. Fair enough? And that's called, this thing, we're showing this string vibrating at what's called its fundamental frequency, the lowest frequency that meets our criteria for a standing wave on a string, that there has to be a node on each end. Okay? Now, that's not the only way we can make it work. Here's the only thing that has to be true. You have to have a node on each end. So there are other waves that can meet that criteria, and we call those harmonics. And so, for example, if we still want to have a node at each end, we could make it look like this, right? There's a node at each end. But instead of, well, here, we had the length of that string, I hope you can notice, is a half of a full wave, right? If we have just the peak, we have only half of a wave. That length, L, of the string is half a wavelength. Notice that here, the same length of the string now gives us two half wavelengths, a full wave. So therefore, we call this the second harmonic. Yeah? Let's look at another case that works. Again, all we need to really have is a node on each end. Well, there's a node on each end. This is now where the length of the string, L, is 3 half wavelengths. And therefore, I call this the third harmonic. Fair enough? Unfortunately, I don't have a good sample problem in here, but we're going to go through some tomorrow when you get back to class. Okay? This this is what we call standing wave on a string scenario. Okay. We have a guitar here. If anyone wants to bring their guitar and/or string instrument, please do. Okay, please do tomorrow. Now, the other thing about strings is we can also, like we showed you with the spring, we can, what am I getting at here? We can change how the wave travels on a string. Now, we want to look at a little more about strings, like we said, and we know now the criteria for what has to be true for a standing wave on a string. Well, you have to have a node, a part that doesn't oscillate on each end, right? Sure, that's always true. Now, but we can create, different pitches on different guitar strings, let's say, right? And how do we do that? Well, we're really saying, what do we have to actually change about a guitar string to make a different pitch? Well, there's two things. If you can think of a guitar, what is it that changes when, a high string and a low string? Well, they look different. All right, that's one thing. And because, well, there's the other thing. The first thing that I'll say is they have different linear densities, right? And that says literally like a thicker string sounds different than a thinner string. Or literally, linear density refers to the mass per unit length. The other thing, like we mentioned today, was that if we want a string to change its pitch, we can tighten it or loosen it. We can change the tension on the string. All right, so those things also have a big effect on what frequency a string vibrates at. Right? Let's write an expression for wave speed based on these two factors. All right, well, here's the deal. We know for any wave in any medium, we know this. V is F times lambda. Now, for a string, wavelength only depends on how long the string is. Right? I mean, if there's a string this long, well, you could get our fundamental frequency, no matter what, is going to look like that. Right? No matter, every string that has that same length is going to have that same, length of its fundamental vibration. Right? Regardless of its tension and linear density. All right, so we're saying basically that wavelength is something that stays the same. So let's change this. It changes. So if we want to increase frequency, what we have to do is change the speed of the wave. All right, if we want a string to vibrate at a higher frequency, we got to make the wave travel faster on it. All right? So, if we want to increase pitch, here's what we do. We increase tension. So, like we said, increasing velocity makes frequency increase. How do we do that? Well, that's proportional to how much tension's on the string. A more tightly pulled string, I guess you could say, vibrates at a higher frequency. The wave travels faster on it. Okay? Now, also, this linear mass density thing, what do lower pitch strings look like? Well, they're fatter. They're fatter strings. So that means that, the bigger the linear density, the slower the speed. The lower the frequency. That means these are inversely proportional inversely proportional to what we call mass over length. This, literally, this is mass over length. So that means we can write a different expression for wave speed, and it looks like this, right? For a faster wave, we want a bigger tension, but for a faster wave, we want a smaller density string. Well, if you work the units out, you'll notice that we have to have a square root in here to make this work. So this is a new expression only for strings for the speed of a wave on a string. What we call it, the square root of T over M over L. Okay? Sometimes some questions or expressions will write that as a separate variable, like rho or something like that. We just write it in AP as M over L. Okay, so yes, there's our expression for wave speed based on those two factors. Whoops. Okay, so there's two things. We can now do a whole bunch with talking about, going back to here. Sorry, this will take a couple minutes. But going back to here, questions like this, we can talk about, okay, I've got a string of a certain length, and, which harmonic is present. Well, that tells us, what the wavelength is, and then we can go here, and if we know, the mass of the string and its length, then we can relate, what frequency will the thing oscillate at. So we can do some pretty complex standing wave problems now with our new understanding, hopefully, of the reliance of wave speed on some other stuff, and what criteria we need to form standing waves on strings. I wish I had a good example problem in here for you, but I do have a bunch that you'll see when we sit down tomorrow. Okay, folks? Okay, see you soon.